Hello, this is Dr. Hanaa Assil, and this is the second part of the review on Modular Unit 2 for the IGCSE Chemistry Edexcel. So, let's talk about different types of structures. We said molecules could be simple molecular structures such as water, carbon dioxide, small molecules with weak attraction forces between the molecules, and that means they have low melting point because they need only a small amount of energy to be separated from each other. So simple molecular structures have low melting point because they have weak attraction forces between molecules that need a small amount of energy to be broken. Remember that the larger the molecule, the higher the melting point. So melting point increases with increase in the molecular mass. Now, if something is not simple molecular, it is giant macromolecular structure. Remember that the word macromolecular means giant, large, three-dimensional structure with many atoms strongly bonded together. Now, which molecules are giant or macromolecular? You should know ionic crystals are giant crystal lattice, three-dimensional structure with alternating positive and negative ions. Metallic structure, we said these are giant again with a lot of positive ions surrounded by delocalized electrons. Diamond and graphite are giant covalent molecules. Also, silicon dioxide is a giant structure. So, if we want to describe the structure of any metal, it is giant three-dimensional structure with regular rows of closely packed positive ions surrounded by a sea of delocalized electrons. Each of these atoms has one or two or three electrons in its outer shell. It doesn't really want it. So these outer electrons are just floating around. So we say they are a sea of delocalized electrons. Remember that metals have high melting points and boiling points because of the strong electrostatic attraction forces between what? Between positive ions and negative electrons. If we're talking about a metal, it's made up of positive ions and negative electrons. So it has high melting point because of the strong attraction forces between these. Now, if we're talking about physical properties of all metals, you should realize that all metals conduct electricity because they have free moving delocalized what? Metals conduct electricity because they have free moving electrons. Remember, ionic compounds conduct electricity when they have free moving ions. Metals have free moving electrons. Now, metals are malleable and ductile because layers of positive ions can slide over each other when heated or hammered. Do not say there is weak attraction forces between the layers. That's not it at all for metals. For metals, the layers of positive ions can slide over each other when heated or hammered, so that's why they're malleable and ductile, and of course all metals are shiny. Now, the giant non-metals are diamond, graphite, and fluorine. These are all different forms of carbon, and you should know that diamond is giant three-dimensional structure in which each carbon atom is covalently bonded to how many? To 4 other carbons in a rigid tetrahedral structure. That's how you explain the structure of diamond. What about graphite? Graphite, again, giant three-dimensional structure in which each carbon atom is covalently bonded to 3 other carbon atoms in layers of 6-sided rings with weak attraction forces between the layers. This is where you say weak attraction forces between the layers. So if we're comparing diamond to graphite, diamond is hard. Why? Because of its structure. So because of strong covalent bonds between carbon atoms in the rigid 3-dimensional tetrahedral structure. Why is graphite soft? Weak attraction forces between the layers allows them to slide over each other or slide past each other. Diamond does not conduct electricity. It does not have free electrons. Graphite conducts electricity because it has free delocalized electrons, not ions. The only time we mention ions is if we're talking about ionic compounds. Graphite conducts electricity because of free moving delocalized electrons. Diamond, because it is hard, it is used in cutting and drilling equipment. Because it is hard, and it's hard because it has strong covalent bonds between carbon atoms in the rigid 3-dimensional tetrahedral structure. Now, what do we use graphite for? Please do not say for pencils. We know that graphite is what we have in pencils, but when we say what do we use graphite for, we use it either as a lubricant because it is soft, because of the weak attraction forces between layers that allows them to slide over each other, or we could say that graphite is used as electrodes because it conducts electricity. Silicon dioxide is giant, 3-dimensional, and it has a structure very similar to diamond. So giant, 3-dimensional tetrahedral structure, but remember diamond is made up of carbon, so it's an element. Silicon dioxide is made up of silicon atoms and oxygen atoms, so this is a giant covalent compound. Giant 3-dimensional tetrahedral structure in which each silicon atom is covalently bonded to 4 oxygen atoms, and each oxygen atom is covalently bonded to 2 silicon atoms. Please learn all of these things. Silicon dioxide is solid, but carbon dioxide is a gas, and both silicon and carbon are in group 4. So why is it that silicon dioxide is a solid but carbon dioxide is a gas? This is because the carbon dioxide is simple molecular structure, weak attraction forces between molecules. But silicon dioxide, giant 3-dimensional tetrahedral structure with many strong covalent bonds. Fullerene is another form of carbon, but it is something that has only 60 carbon atoms, so it is regarded as a small, simple molecular structure. So fullerenes are structures made up of 60 carbon atoms joined together in pentagons and hexagons. Since they are regarded as simple molecular structures, they have low melting point, so they're not as high as graphite and diamond, because they have weak attraction forces between the molecules that need a small amount of energy to be broken. Any question that says, why does anything have low melting point? That's probably due to weak attraction forces between molecules that need a small amount of energy to be broken. So, for example, this was a question about fullerene. It said doctors use fullerene to deliver medicines to certain parts of the body so that the medicine does not damage other parts of the body. Why is C60 fullerene suitable for this purpose? Usually, fullerene is used in medicine because it will not react and it is non-toxic. Titanium chloride and titanium oxide are both covalent compounds, but we are told that TiCl4 is liquid while TiO2 is solid with high melting point. So when he says something is a liquid, that's probably because it has simple molecular structures with weak attraction forces between molecules. If something has a high melting point, then it is giant, and we're told it's covalent. So the TiCl4 is a simple molecular structure with weak attraction forces between molecules, because I am told that the melting point is low. This needs a small amount of energy to be broken. Now, we are told that TiO2, the melting point is high. That means it is giant covalent structure with strong covalent bonds that need a lot of energy to be broken. Okay, let's talk about electrolysis. What is electrolysis? It is the breakdown of an ionic compound, molten or aqueous solution, by the passage of electricity. So what we have is, we have an electrolyte, which is an ionic compound, molten or solution, so it has positive and negative ions that are free to move. So that is the electrolyte, molten or aqueous solution that can conduct electricity. We also have rods that are placed into this solution. The rods are called electrode, and the electrode is made of a substance that conducts electrons. So the electrodes are connected to the ends of the battery. The electrode connected to the positive end of the battery is positive, because electrons in the wire are attracted towards the positive end of the battery. Now, the electrode connected to the negative end of the battery is negative, since electrons in the wire are repelled away from the negative end of the battery, so they accumulate on that electrode. Now, that means that the ions in solution, positive ions or cations, are attracted to the negative electrode, so that is called cathode. The negative ions or anions are attracted to the positive electrode, so that is called the anode. And what happens is, metals or hydrogen are formed at the negative, because these are the ones that were positive ions, while the non-metals other than hydrogen will form at the anode, because these were the negative ions. And then we said before that ionic compounds conduct electricity when molten or in solution, but not when solid, and that is because ions are free to move when they are molten or in solution, but when solid, the ions are fixed in the three-dimensional crystal lattice. So, if we do electrolysis of molten sodium chloride, first of all, you should know that sodium chloride, the first one is always a positive ion and the second one is a negative ion. So that means I have in my electrolyte Na plus and Cl minus. Now we said that the negative ion goes to the positive electrode, so the chloride will go to the anode. Now go to the anode and do what? Lose electrons. So the negative ions go to the anode, lose electrons. You should remember that loss of electrons is oxidation. So the chloride ions go to the positive anode, lose electrons and become chlorine atoms. And then the atoms join together and form molecules. While at the cathode, the positive ion goes to the cathode, gains electrons. Gain of electron is reduction, and what is formed is sodium atoms. So if we say name the product at the anode, chlorine gas. Name the product at the cathode, sodium metal. Now, what is observed? Remember the question that says what is observed means we need to say what do we see. So when the question says what is observed, don't say chlorine gas. What do we see when chlorine gas is formed? Remember that chlorine gas would be seen as bubbles of green gas. So that is our observation at the anode. What is the observation at the cathode? It is forming sodium. So what do I see? I see silvery gray metal. Are we okay with all of this? So let's try again. If we're doing electrolysis of molten lead to bromide, again, which one is the positive and which one is the negative? Remember, the first one is the positive, or the metal is the positive, and the non-metal is the negative. And please remember that lead, if you look for it in the periodic table, it's actually in group 4. But this is an exception. It doesn't have valency of 4, it has valency of 2. And we always write it as lead 2 to indicate that we're talking about Pb2+. Now, what happens? Of course, we said the negative ion goes to the anode and loses electrons. And that means it changes from bromide to form bromine. Now, you should know that bromine originally is reddish brown. And originally it is a liquid. But remember that to get the lead bromide to be molten, we had to heat it to a very high temperature. So if we say what is observed at the anode, it is reddish brown fumes or reddish brown gas. At the cathode, the lead2+ gain electrons and become lead. So what is observed? Again, a silvery gray metal. So, if a question says, explain why the electrolytic cell containing lead bromide needs to be heated before electrolysis can occur. We said, if I have lead bromide as a solid, I have to heat it until it melts, because the lead bromide needs to have free moving ions to conduct electricity. So the lead bromide needs to be heated until it melts so that ions are free to move in order to conduct electricity. What if we're doing electrolysis of copper to chloride? Again, positive ions go to the negative ion goes to the positive. So the chloride again goes to the positive, loses electrons and becomes chlorine gas. So name the product at the anode, chlorine gas. What is observed at the anode? Bubbles of green gas. At the cathode, the copper 2+ gains electrons, becomes copper. So if we say name the product, it's copper. What is observed at the cathode? A reddish metal, or we say reddish brown solid. Then if we talk about electrolysis of aqueous solutions, now we have, in addition to the ions, we have the ions from water. So if we're doing electrolysis of concentrated HCl, we have H+ and Cl- from the HCl, but we also have H+ and OH- from the water. And that means we have a choice at the anode between chloride and hydroxide. When we have a choice between chloride and hydroxide, the one present in larger amounts is the one that reacts. So we are talking about concentrated HCl. That means we have more chloride ions, and that means that is what would react at the anode. Chloride loses electrons and forms chlorine gas, which is seen as bubbles of a green gas. At the cathode, the only positive ion we have is H+. It gains electrons and becomes hydrogen gas, and hydrogen gas form bubbles of colorless gas. Concentrated sodium chloride solution. What are the ions that we have? Na+ and Cl- in addition to H+ and OH- from the water. Again, which one would work at the anode? This is concentrated solution. We have a lot of chloride. It is the chloride that will lose electrons and become chlorine gas at the anode. Now, at the cathode, we have a choice between Na plus and H plus. Remember, when we're choosing between chloride and hydroxide, it was the one present in larger amounts. But when we're choosing between Na plus and H plus, it is always the H plus that reacts. The one that is lower in the reactivity series is the one that works in electrolysis. And that means in the concentrated sodium chloride solution, chloride has reacted at the anode, H plus has reacted at the cathode, and we are left in solution with sodium hydroxide in the solution. So remember, when we do electrolysis of concentrated sodium chloride solution, we are left with sodium hydroxide in the solution. So this is a question about electrolysis of sodium chloride solution, and the question says, explain how hydrogen gas forms at the negative electrode. First of all, hydrogen gas is H plus, so H plus goes to the negative electrode because it's positive ions. Now, when the H plus ions go to the positive electrode, they gain electrons, form hydrogen atoms, and then the atoms combine to form hydrogen molecules. This is how we explain how each of the products is formed at the different electrodes. What if we're doing electrolysis of dilute sodium chloride? Now, dilute sodium chloride still has the same ions, Na plus Cl minus and H plus OH minus. Now, which one is going to react at the anode? Remember, we're choosing between chloride and hydroxide, and we said the one present in larger amounts is the one that will react. Now we have a dilute solution, and that means I have more OH minus, I have more water. And when the OH minus reacts, it forms oxygen gas, which would appear as bubbles of colorless gas. It forms water and it releases electrons, and please notice the balancing. What about at the cathode? At the cathode, again, I have a choice between Na plus and H plus, and we said between Na plus and H plus, it is always the H plus that reacts, gains electrons, and becomes hydrogen that is seen as bubbles of colorless gas. What about electrolysis of aqueous copper sulfate? So we have copper 2 plus, sulfate 2 minus, and H plus and OH minus. Now at the anode, we have a choice between sulfate and hydroxide. I want you to remember, sulfate never reacts in our syllabus at any of the electrodes. So sulfate is not going to react. It is the OH minus that reacts. And we said when the OH minus reacts, it gives oxygen plus water plus electrons. Please notice the balancing. Now, what about at the cathode? At the cathode, which one is going to react? We're comparing between copper ions and H plus. Remember, we said in the electrochemical series or in the reactivity series, the one that is down is the one that reacts in electrolysis. So which one is less reactive, or which one is at the bottom of the reactivity series? It is the copper. So it is the copper ions that will gain electrons and become copper. And that means in the electrolysis of copper sulfate solution, the OH minus reacts and the Cu2 plus reacts. what is left in solution? We have H plus ions and sulfate ions. That means our copper sulfate solution changed into sulfuric acid. You should remember that copper sulfate originally is a blue solution. It's going to change to sulfuric acid, and that means the blue color will disappear because any acid is a colorless solution. What if we're doing electrolysis of dilute sulfuric acid? Again, at the anode, I have a choice between sulfate and OH minus, and we said always it is the OH minus that would react when compared to sulfate. On the other electrode, we have only H plus ions that take up electrons and become hydrogen. So this is a question on electrolysis of concentrated solution of sodium chloride, and we're given two equations. Please notice that the equation given at the negative electrode is different from what we wrote. We wrote H plus electrons to give hydrogen gas. Here he's writing it in a different way, H2O plus electrons to give hydroxide ions plus hydrogen gas. Then the question says, state how these ionic half equations show that equal volumes of the two gases should be collected. Now, if you look at the two equations, they both have the same number of electrons. Remember that in order to compare, these are called ionic half equations, and in order to compare them, they must have, first of all, the same number of electrons. Now, based on these equations, the first equation gives 1 mole of hydrogen. The second equation also gives 1 mole of chlorine. So from the equations, because the number of electrons are the same, the number of moles of the gases can be compared, and this gives the same number of moles of hydrogen and chlorine. Then the question says, suggest why the volume of chlorine collected is less than expected. If you look at the diagram, we just said that based on the equations, we should have equal volumes of hydrogen and chlorine. Can you see that the hydrogen is much more than the chlorine collected at the top of these tubes? Why? Where did the chlorine go? Remember that chlorine dissolves in water, so some of the chlorine dissolved in the solution. Okay, this is a similar type of question where we're talking about electrolysis of dilute sulfuric acid. We are given two equations, so the H plus gains electrons and becomes hydrogen gas, and the OH minus loses electrons and forms oxygen gas. The volume of hydrogen gas collected after a few minutes is shown on the diagram. So he already gives me the volume of hydrogen gas collected in that test tube on the left. Draw another line on the diagram to show the volume of oxygen gas collected after the same length of time. We said in order to know the relative volumes of these gases, we look at the two equations. But in order to compare the two half equations, we must have the same number of electrons. Are the number of electrons the same? Of course, equation 1 has only 2 electrons, while equation 2 gave 4 electrons. So what should we do to equation 1 to make the number of electrons the same? Multiply through by 2. So this makes 4 electrons. Now we can compare the two equations. And from the equations now we can see that the first equation gives 2 moles of hydrogen and the second equation gives only 1 mole of oxygen, and that means the volume of oxygen should be half the volume of hydrogen. So look at the diagram up there. We have drawn a line to indicate that the amount of oxygen collected in the test tube on the right is about half the volume of hydrogen in the other test tube. Of course, the explanation is when the number of electrons are the same, the number of moles of hydrogen is twice that of oxygen, so twice the volume. Okay, and then we're supposed to talk about the periodic table, groups 1 and group 7. Okay, so remember that when we look at the periodic table, all the elements that are in the same group have similar chemical properties because they have the same number of electrons in outer shell. So all those in group 1 have 1 electron in their outermost shell. Their chemical properties will be similar. Also group 7 all have 7 electrons in their outermost shell, so they will behave similarly to each other. So group 1, what is the name of elements in group 1? You should know that these are called alkali metals. The ones in the middle there are transition metals. The ones in group 7 are called halogens, and the ones in group 8 are called noble gases. So group 1 are called alkali metals. We already know that because they're in group 1, they all have 1 electron in the outermost shell. They are also very reactive metals. They are the most reactive metals in the periodic table. So anything in group 1 is much more reactive than group 2 or group 3, and that is why they have to be stored under oil. So if we're asked why are they stored under oil, because they're very reactive, so this prevents any reaction with oxygen or water vapor in the air. They are also soft metals so that they can even be cut with a knife. So remember that these are soft metals. Remember that reactivity increases going down the group. We said the one at the bottom of the group is much more reactive than what's on top. We say that cesium is the most reactive metal. Remember, we ignore francium completely because actually francium is in that group because it has 1 electron in its outermost shell, but it actually has different characteristics from group 1. So just ignore francium. Cesium is the most reactive metal. So going down the group, you should realize reactivity increases, density increases, but melting point decreases. So please remember that lithium, when we put lithium, for example, in water, it would react, give bubbles of hydrogen gas. Sodium is much more reactive. Potassium will explode or will be very vigorous if you put it in water. So going down the group, the metal becomes more reactive, higher density, but melting point of lithium is higher than cesium. Now, the question is, why is it that as we go down the group, reactivity increases? Remember that reactivity of a metal depends on how easily it can lose the outer electron. So if a metal can lose the outer electron easily, it is more reactive. So if we look at lithium, which one, or lithium and potassium, which one would lose the electron more easily? Remember that lithium is a small atom. The electron is very near to the positive nucleus. Strong attraction forces between the negative electron and the positive nucleus, so it is not easy to lose that outer electron. While as we go down, potassium, for example, the outer electron is further away from the nucleus, less attraction forces between the negative electron and the positive nucleus. So as we go down the group, it is easier to lose the outer electron, so the metal is more reactive. So Reactions with oxygen, all metals react with oxygen, and when they react with oxygen, they form oxides. And of course, as we go down, more reactive metals react more vigorously with oxygen. And the oxide that is formed is the oxide of a metal, and we know that oxides of metals are usually basic. This is because when they are dissolved in water, they form hydroxide ions. Remember, if we're asked why is something basic or alkaline, it is because when dissolved in solution, it forms hydroxide ions. So magnesium, for example, magnesium burns in oxygen to form magnesium oxide. And you should know that magnesium burns with a bright flame, or we say with a white flame. If we talk about flame color, we're going to say that magnesium doesn't have any flame color. It gives a white flame. And the magnesium oxide that is formed is a white solid. So these are the observations when we burn magnesium in oxygen. Sulfur also burns in oxygen, and remember that coal contains sulfur impurities, and sulfur is a nonmetal, but also when it burns, it forms the oxide, and this oxide is acidic. Remember, oxides of nonmetals are acidic in general, so that when they dissolve in water, they form acid. So the sulfur dioxide formed can be oxidized sulfur trioxide. You should remember that sulfur trioxide dissolves in rainwater to form sulfuric acid, and that is what we call acid rain. What about reactions with water? You should realize that the very reactive metals can react with cold water, and when they react with cold water, they form the hydroxide plus hydrogen. So potassium plus cold water will give potassium hydroxide plus hydrogen, sodium plus water, sodium hydroxide plus hydrogen, and so on. But starting from magnesium till above hydrogen, these are less reactive metals. They don't react with cold water, or they react very slowly with cold water. So we react them with steam. So that's just water at very high temperature. Now, a metal that reacts with steam will give the oxide plus hydrogen. So magnesium plus steam, magnesium oxide plus hydrogen, zinc plus steam, zinc oxide plus hydrogen. Of course, anything below hydrogen in the reactivity series will not react with water and will not react with acid because it is less reactive than hydrogen. So looking at potassium, potassium is very reactive. We put it in cold water. First of all, you should realize all group 1 have low density or lower density than water, so they will float. So potassium will float. It reacts with water to give what? To give potassium hydroxide plus hydrogen. That means it is giving off bubbles of gas. These bubbles push the piece of potassium around, and as the potassium reacts, it starts to disappear, or we say it melts. Potassium is very reactive, so the fizzing is very vigorous, and the bubbles of hydrogen gas catch fire. And remember that when potassium catches fire, it gives a lilac flame. This purple shade of purple is called a lilac flame. Sodium is a little bit less reactive. So when we put sodium in water, again, sodium will float, dart, melt, or disappear. Now we also have vigorous fizzing, okay? If you're going to compare the sodium to the potassium, then the potassium is more vigorous, very vigorous, or we could say violent. Remember, violent is more than vigorous. And the solid sodium disappears because it is used up. The bubbles of hydrogen gas may catch fire. So we may find a small piece of fire darting around or moving around on the surface of the water. Remember that the solution formed is a solution of sodium hydroxide. That is alkaline. So if we were to put litmus paper into the solution at the end of the reaction, it will turn from red to blue. What about calcium? Calcium is less reactive than sodium. So calcium, again, it reacts with cold water to give the hydroxide plus hydrogen. But then calcium is in group 2. So calcium sinks, it doesn't float. And as the piece of calcium reacts, it starts to slowly disappear, or we could say it gets smaller. Now we have strong fizzing. Don't say vigorous, don't say violent. So if we're comparing, potassium could be regarded as very vigorous or violent. Sodium, vigorous. Calcium, strong fizzing. And the solution becomes milky because the calcium hydroxide that is formed is not very soluble in water. So as the calcium hydroxide is being formed, the solution becomes cloudy. What about magnesium? We said magnesium, if we put it in cold water, the reaction is very slow. So we react it with steam. Magnesium with steam forms magnesium oxide plus hydrogen gas. So the magnesium oxide is formed, and magnesium oxide, you should know, is a white solid. And of course we have bubbles of hydrogen gas that is formed. Zinc also reacts with steam to give zinc oxide plus hydrogen gas. What about acids? We said any metal above hydrogen would react with acid. Any metal more reactive than hydrogen would react with acid. So magnesium reacts with acid to give the salt plus hydrogen gas. Remember, and the number of bubbles of hydrogen gas, or how fast the bubbles are formed, is an indication of the reactivity of the metal. So if I'm comparing magnesium to zinc, for example, you should realize that magnesium is more reactive than zinc, so the bubbles in magnesium will be more than those in zinc. Now, copper is below hydrogen in the reactivity series. It is less reactive than hydrogen, and therefore it will not react with water or with acid. So if we put a piece of copper in water, no bubbles, no reaction, no change. Remember that a more reactive metal would displace a less reactive metal from its salt. So if we put zinc in copper sulfate solution, you should remember that copper sulfate solution originally is blue. Now, zinc is more reactive than copper, so it would displace the copper. So the copper sulfate solution will change to zinc sulfate. Now, zinc sulfate solution is colorless. So one of the observations that we see is that the blue color of the solution disappears. The piece of zinc will disappear or dissolve, and we're forming copper, and you should remember that copper is a reddish brown metal, so we can say a red precipitate or a reddish brown solid is formed. What about group 7? Group 7 are called halogens. They have 7 electrons in their outermost shell. They are the most reactive non-metals. And remember that in group 7, the one up is more reactive. So the most reactive non-metal in the periodic table is fluorine. You are required to know the appearance of each of the group 7 elements. So fluorine, you should realize that fluorine is a yellow gas, chlorine is a green gas, bromine is a reddish brown liquid, iodine is a gray solid, and astatine is a black solid. Notice that as we go down the group, the color gets darker, the state changes from gas, liquid, solid. And if we look at iodine, iodine is unique in that it has different appearances. As a solid, it's gray. Now, if we dissolve it in solution, remember this would be iodine solution that we use to test for starch. Iodine solution is a reddish brown solution. Now, if we heat the gray solid, it sublimes. Remember, sublimation means it changes from solid to gas directly. And when iodine sublimes, the vapors are violet vapors. So, as a solid, it's gray, in solution, reddish brown, and as a gas, it is violet vapors. Remember again, we said the one up in group 7 is most reactive. As we go down, we said the color gets darker, density increases, and melting point increases. Remember, we're changing from gas, liquid, solid. That means the ones down have higher melting and boiling points. Now, the more reactive nonmetal again displaces the less reactive nonmetal from its salt. So, if we look at this reaction, chlorine plus potassium bromide. Now, we should know that chlorine is more reactive than bromine, so it will displace it. So, if I start with potassium bromide solution, and you should remember, potassium bromide is a compound of group 1 that is colorless solution, no color. Now, when we add chlorine, the chlorine will displace the bromine. So we start to form bromine, and you should realize bromine is an orange solution. So slowly the colorless solution becomes orange. And that is because what we're forming is bromine plus potassium chloride. Now, if we react chlorine with potassium iodide, again, chlorine is more reactive than iodine. And that is why when we put chlorine into the colorless solution of potassium iodide, the iodine is formed, so we get a reddish brown solution. But if we say iodine plus potassium bromide, you can see that iodine is less reactive than bromine and cannot displace it, so no reaction. We said group 7, the one up, is more reactive. Now, why is that? You should realize that for non-metals, the ability to gain electrons determines how reactive it is. Remember, we said in group 1, the ability to lose an electron. And that is why as we go down, the metal becomes more reactive. But in non-metals, they want to gain. So the ability to gain, if it's more able to gain electrons, then it is more reactive. So we said fluorine is the most reactive non-metal. And that is because at the top, the atom is small. So chlorine, for example, is small. The incoming electron will be nearer to the positive nucleus, strongly attracted to the positive nucleus, so the electron is easily gained. While as we go down group 7, the atom becomes bigger. So the incoming electron is further away from the nucleus, less attraction between the negative electron and the positive nucleus, so the electrons are less easily gained. Okay? And this is the end of this second part of the review on Modular Unit 2. We still have the rest of it in the next review. Thank you for listening.